and that is heat aging of rubber materials. And the factors which influence is the test results. I also sent out the technical report, which I wrote some years ago, but I have been working with, say, developing and looking into what factors influence the test results when doing aging tests. I started over 30 years ago with that, and we have continued to look into the problems to see how we can make the best instruments for testing heat aging. We started quite early with a project when I was still working at the National Testing Institute, where we looked at how to improve the testing. And aging was one of the tests we looked at. And we made the so-called interlaboratory comparison with 12 laboratories. But we were very, very, very disappointed of the results. We will look more at that later on. If we look at the ovens which have been used for testing of rubber, the one to the left is a cell oven, still specified in ASTM. I think people understood quite early that you needed a very stable temperature and you needed to separate the samples. That's why a big aluminium block was used and separate test tubes for each material. The small tubes in the picture there was an idea that you need to change the air to keep the oxygen concentration constant. But it's not possible to measure how much you change the air in that setup. And of course, you needed a huge aluminium block because in the old times the temperature controllers were not so accurate as today. To the right, you see a slightly more modern, but still an old design. It's a cell oven with bigger cells and controlled air exchange by an air pump. And there are 7 cells, and you can then have the materials in each material, one material in each cell. But even here, there were some problems with the accuracy. The problem with that type of oven is the preheating of the air. So the air was a little too cold when it came into the. Look at cabinet ovens. Let's say originally there were no cabinet ovens really meeting the requirements for heat aging. Here are some we looked at that project we made, where we took cabinets from some of the participating labs and we measured them. These were standard lab ovens. So you can see they normally have a fan in the back, which means that it blows quite high air speed, especially in the center and in the sides. So the air comes out on both sides around the baffle and sucks in the center. And then you have 2 places, there will be 2 circles of air. And in the middle, it's very low airspeed. And a very early test I did was to take in steel wire, put samples over the whole width of the oven, or such an oven, and we could see that we got different aging results depending on the location in the oven. There are also, say, ovens used without the fan to have a low airspeed, and that is used in the cable industry. In the IEC standards, they specify that there should be a low airspeed, no fans, and then they use ovens with so-called gravity convection. But to get gravity convection, it means that you need a temperature difference in a different part of the ovens. And that difference in temperature gives an say exchange of the air. But to keep the temperature within plus minus say 1 Celsius, you have to measure the temperature inside the oven and find the space in the center where you have say 1 liter or something of the volume where you can have a constant temperature. And of course, then you need maybe a 60-liter oven and you have 1 liter test space. And the IEC also specifies that you place an extra temperature sensor close to the samples. So their idea is good, but it's wasting a lot of space. We designed a couple of ovens. Originally, for rubber testing, cell lading ovens were very common and described in the standard. And the cells here are 100 millimeter in diameter and 300 millimeter high. And you see the test specimen holder laying on the top of the oven. There is also an air pump which feeds air of the specified amount of 3 to 10 changes per hour into each cell. Then we designed a cabinet aiding oven, and that is more difficult to get a good temperature uniformity in the whole space. And on these 5 ovens, we did a lot of measurements. Among other things, we made an interlaboratory test program. It means that we compared the results of, I think it was 3 materials, 12 laboratories, and we measured tensile strength and change in hardness. Here is just a kind of average summary of all results. You can see that the tensile strength, the mean change was minus 18%, but the big R, which is the reproducibility in actual units of measurement, that is percent in this case, is almost as large as the mean change. And the R in parentheses is the percent of R calculated on the mean change. So it's quite high. The most important property when you check aging is in fact the elongation at break, because that always goes down and will be lower with aging. That was reduced 40% with an absolute R of 16%, and the percentage between these two are 40%. If we look at micro hardness, IRHD, the hardness went down 13 degree, and that is the same as the R, and is 10 hardness degrees between different labs. So the big R is the difference between the lab with the, say, the range from the lab with the lowest result to the lab with the highest result. This is of course not very well, it's bad. Let's go further. We then decided to investigate different ovens and their uniformity in time, uniformity in space, air speeds, air exchange rates, and practical aging results in different ovens. If we look at the tolerances we have in the standards, we tolerate plus minus 1 Celsius up to and including 100. Over that we have plus minus 2 Celsius. And for time we have plus minus 2 hours if the test time is 1 week or longer. But already 1 degree wrong temperature corresponds to roughly 10% in testing time. If we use the rule of thumb with an Arrhenius factor of 2, or is the Arrhenius factor higher? It could be up to 15%. So this means that 2 labs can be quite apart and still be within the specification. That is why we later on introduced in the ISO standard the requirement of having a temperature sensor close to the samples and try to set the temperature as exact as possible where the samples are located. two factors we investigated close, and that was the temperature and air speed. The air exchange rate had already been investigated in an ISO project where we ran interlaboratory tests, where we had the air exchange of 0, 3 times, and 10 times per hour. The standard has specified 3 to 10. We found that there was very little difference between 3 and 10 time air exchange, but if we had no air exchange, we got dramatically different results, or much better results, because the oxygen concentration went down and the aging went slower. So it's always important to have air and having the same concentration of oxygen, but also ventilate away degradation products. The ovens we measured were these ovens, 2 our own ovens and the ovens which were very much used in the rubber industry in Sweden at that time. We looked at the temperature variations in time, and they were all good except one oven, but that oven happened to be an old oven with a bimetal thermostat and not an electronic thermostat. So as long as we have some electronic thermostat, they can keep a constant temperature quite good. But to the other thing is that the temperature variations in space. There we measured in 15 locations, but we could only measure 5 at the time. So we had a frame where we had temperature sensors in each corner and 1 sensor in the center. And that frame was then placed inside the oven 50 millimeters from the back wall, then moved to the center of the oven, and then moved to 50 millimeters behind the door. And there were the differences, as you can see, if you take the total 1.2 degrees, 1.7, 3.1. The oven with 3.1 had a window in the door, and behind that window, 50 millimeters behind the window, it was much cooler than in the rest of the oven. Our own ovens, they are in the range of, say, 0.5, 0.4 degrees. Another test we made was that we put a PT100 sensor in the center of the ovens. Then we adjusted the oven so that sensor showed 100 Celsius. And then it happened that the set point was quite different. And the temperature shown on the oven were also sometimes not the same as the set point, but they were all different from the 100 in the center, except for our own ovens where we can keep it quite close to the desired temperature. You can see some measurements here, and the first part of the curve is inside the oven, close to the back. Then we open the door and measure in the center of the oven. Then we open the door again and move the temperature, the frame with temperature sensors to the 50 millimeter behind the door. And there we see the influence of the window, that is the lowest temperature, just in the center, inside the window. Here is our own cabinet oven, where we have a difference of plus minus 0.2 degrees, and the last part of the curve is plus minus 0.1 degrees. And that is in the range of so the measurement error. And we come to air speeds. We measured the air speed at a lot of different points in the chambers, and we found that there were quite variation depending on where we measured, from almost 0 to quite high air speeds. The speeds are given in meters per second, and that explains the result we got when we tested at different, say, the aging on rubber samples on different positions. that we got quite different results. Another thing is the air exchange rates, and it's difficult to set on a normal lab oven, and it's even more difficult to measure it. But sometimes they can have a throttle you can set to 0 and you can open it, and that can be dramatic difference in the air exchange between closed and open. Of course, in an aging oven you need to know. So there, in our ovens we use a flow meter with a needle valve so you can set the desired air exchange rate. Here we have the customer who had a problem with a nitrile PVC compound for automotive customer. They did 8,000 hours required by the customer, and then the micro hardness was measured, among other things, and the maximum tolerance of micro hardness was increasing of 15 degrees. But he got 17 degrees when he did the aging in a normal, the normal oven he'd been using for aging. Then we did a test in our cell oven where we have a low air speed, and we found that the red curve that the hardness were increasing on a steady state in both cases, but in the blue curve had already peaked after just a little more than 300 hours. So we got an increase in hardness of 13 degrees. And then the customer could say that the compound met the requirement of the customer without doing more than buying an aging oven, which did a more correct aging. Or perhaps he could have waited a little longer. Then maybe the blue curve had dropped down to below 15 as well. But that is a little cheating then. What we did then to examine the air speed influence. We designed ovens with a laminar air speed of 0.3 and 3 meters per second. The blue line is our cell ovens or our cabinet ovens where we have the air speed is only dependent on the air exchange rate. That means it's in the range of 1,000 meters per second. So we can see that the higher air speed, the more we lose in weight. In this project, we tested 4 compounds. We also tested tensile strength and a lot of other properties. But it's easy to show what happens when you look at the weight loss. We lose something. And what happens is that on the exhaust of the oven, we put in a condensation trap so we could get some condensation and make an analysis. And we found it was not unexpected, by the way, softener and antioxidant. The nitrile has a quite volatile softness. We lost most of it in 3 weeks' time, about 10%. Even at low air speed, we lost weight, but quite less. If we look at another material in EPDM, there we lose much less because the softener is much less volatile. But we still see the difference between the air speed, we lose more. And losing softener and also antioxidants, of course, a change in hardness and change in tensile strength and change in all other properties as well. This work we made many years ago later led to improvements in the ISO standard. We've done that a couple of times. We have the method A, which specify a low air speed, was clarified. There are not allowed any fans in the test space to keep the air speed very low. Also to have a temperature sensor close to the samples. Later on, we have in that standard added the method B1, where we instead have a high air speed but laminar speed. And later on, also method B2 with high turbulent air speed and the carousel. The method B2 especially, I may say, might give even better repeatability and reproducibility in one way. But of course, it's not the same results as you get with method A, because you lose more weight and you have a higher oxidation of the surface as well. If we compare, say, a lab ovens can be quite good today, but they don't have the accuracy in space. They don't have the specified air speed. They have air direction, air exchange rate, and extra temperature sensor. That is only supplied if you buy an aging oven. So we have showed with the experience that what's important is, I think, temperature is the most important thing, air speed, and then air exchange rate. But the air exchange rate seemed to be okay to be 3 times an hour. We can say that in the electrical standards for cables, they have specified 8 to 20 changes per hour, but it's not really needed. And there are standards in ASTM where they specify up to 200 changes per hour. And that is, in my opinion, just a waste of energy. We just need to keep the oxygen concentration constant and ventilate away degradation products. Now coming back to interlaboratory test programs done by ISO. The first we see there is the one we made in Sweden in 1988. There we had a change in tensile strength of -18, elongation of break -40, and the R values are 15, 16. It's quite high. Then in 1996, we have 11 labs in ISO, so participants all over the world, 4 materials. We have less change in percent there. That depends on what materials you use and what temperature you choose. But the R value are still quite high. It's a little better, but not very good. And then we repeated that in 2005, and 3 materials, but unfortunately only 5 labs participated in the method A. At that time in 2005, we also checked method B with high airspeed and method B2. But we see we are in the same range of the R values. They are very close, say around 13 to 15. So in fact, we have not seen any improvement over the years, even if we have improved the requirements in the standard, unfortunately. Of course, the errors we have in the tensile strength measurement, and if you also measure hardness, that uncertainty is added to the uncertainty of the temperature. But tensile tests today are in a much, much lower range of uncertainty than is caused by the heat aging. Then we have made the second, or we are working on the 3rd generation of aging ovens. First we see is a standard cabinet oven. To the right, up to the right, is a cell oven with 4 cells. Down to the left is an oven with a carousel according to ISO the B2 with the turbulent flow. And the one to the right will say down is a cell oven with 6 cells, with each cell having a separate temperature. In the cabinet ovens, if you are testing test pieces, you can hang them on rods, or if you are testing larger pieces, you have shelves you can place on the positions for shelves. To the right, we have a stand where you can easily load your test piece holder for the cell ovens. And we also show that you can put a compression set fixture or jig in the cell oven, or a tension set jig can be placed in the same cell below the dumbbells. So you test, say, both compression set and aging on one material in the same cell. There are some details. You can see the PLC we're now using. You can set the name for each test cell, and you set the temperature, and you can set the timer when it should stop, or you can see how long it has been running. That's quite an improvement. So we avoid all these yellow small labels people put on their ovens when they expect to take the sample out. Now you can put that in the program in the PLC instead. Then we have the oven with a carousel to the right there. And that was more or less what I had to present today. I know it's open for questions. Let's see if you have written any questions in the chat column.